Inside a bead mill, millions of tiny spheres collide thousands of times a second, and with every impact they break a pigment, a drug, or a battery powder a little finer, down past a micron, toward 100 nanometers. The finer the target, the smaller and harder the sphere has to be. Yttrium-stabilized zirconia beads are the media built for that work. Stabilizing the zirconia with a few mol% of yttria locks in a tough tetragonal structure, so the spheres grind hard slurries for hundreds of hours while shedding almost none of themselves into the product. What makes these beads grind fast is mass. A solid density near 6 grams per cubic centimeter, well above alumina or glass, packs more momentum into every sphere, so each collision delivers greater impact energy. That heavier hit lets a mill run at higher solids loading and shorter cycle times to reach the same fineness. A second feature protects what is being ground. With a Vickers hardness around 1250, these beads resist abrasion far better than glass or zircon silicate, where rates fall to a few parts per million per hour. That means the media survives instead of grinding itself into the batch, keeping the finished slurry clean where contamination cannot be tolerated. Two further features keep the spheres whole. A fracture toughness near 8 megapascal-root-metres lets them take repeated high-speed impact without cracking or spalling, even at mill-tip speeds above 10 meters a second. And because zirconia is chemically inert to most acids and alkalis and holds its strength up to around 600 degrees, the same bead works in aggressive slurries and warm mills alike. A single rule governs how fine a mill can go: the size of the sphere. Larger beads leave wide gaps between them, so they strike a given particle less often, while smaller beads pack closer, multiply their contact points, and raise the collision frequency where fine particles actually live. Below 200 nanometers, that frequency, not raw impact, is what drives the grind, which is why nanowork moves to the smallest media. Engineers size the media by a pair of simple ratios rather than by guesswork. The bead is chosen at roughly 10 to 30 times the largest incoming particle, and the achievable target sits near 1/1000th of the bead diameter. A tenth of a millimeter bead, on that logic, drives a slurry toward the 100 nanometer range. The reason bead diameter is specified as tightly as the material itself. Shape matters as much as size. A sphericity above 95% lets the beads roll and shear smoothly, spreading load evenly instead of gouging the mill lining or the separator screen. High uniform roundness also keeps the packed bed predictable, so energy transfers into the slurry rather than into wearing out the machine. Diameters span a wide, well-standardized ladder. Common bead sizes run in steps: 0.1, 0.2, 0.3, 0.5, 0.8, 1, 1.5, 2 millimeters, and reach up toward 25 or 30 for coarse attrition work. At the fine end, sizes from 0.05 to 0.3 of a millimeter are made almost exclusively in zirconia, because no lighter ceramic survives that small. Selection extends beyond diameter. Beyond the yttria stabilized grade, cerium stabilized zirconia serves where still greater toughness is wanted, and the media can be formed as spheres or as short cylinders for particular mills. Outside the standard ladder, diameter, stabilizer content, size distribution tightness, and sphericity can each be specified to a milling requirement rather than taken off a shelf. The application that draws most on these features is the milling of battery-cathode material, the fine dispersion of powders such as lithium iron phosphate and nickel manganese cobalt oxide into a uniform slurry before it is coated onto electrode foil. Here the yttria stabilized zirconia bead earns its place several times over. Ultra-low iron pickup, tight particle distribution, high milling throughput, no shattered fragments, and long, stable service. Contamination control comes first. Iron above 0.5 part per million can fade a lithium cell's capacity for good, and the bead's low wear keeps metallic pickup for below that line. Its high density drives the powder to a narrow submicron distribution that coats evenly and cycles reliably. The same density lifts throughput, while the bead's toughness ensures no shard fractures loose. A single ceramic fragment in an electrode can short a cell, and its wear resistance holds all of this steady across a long production run.